You think you understand reality, the ground beneath your feet, the moon overhead, two separate things governed by separate rules, heaven and earth. That division held for thousands of years until a 23-year-old mathematician tore it apart in his mind. 1666. Cambridge shut down, plague bodies piling in London. Isaac Newton retreats to Woolsthorpe Manor, 60 miles north, and in 18 months of isolation he rewrites the laws of existence. But here's what nobody tells you. The mental process he used. The specific chain of thought that connected a falling apple to the orbit of the moon. The calculation he performed with pen and paper that proved the same invisible force rules everything from a rock to a planet. This is not about discovering gravity. This is about the cognitive leap that unified two realms of reality. The apple story gets reduced to a cute origin myth. He sees fruit fall, he thinks about the moon, gravity exists, end of story. But that sanitized version erases the revolutionary thinking. Newton did not just observe, he constructed a thought experiment that required him to mentally annihilate the boundary between terrestrial physics and celestial mechanics. Between what Aristotle called the sublunary world of corruption and the perfect crystalline spheres, and he did it by asking one deceptively simple question: why straight down? This script is researched and factual, using sources from Newton's own manuscript recollections, held at Cambridge University, particularly his circa 1715 account preserved in the Portsmouth collection, and Edmund Halley's correspondence archived at the Royal Society documenting the Principia's publication timeline in 1687. Now back to the information. Newton sits beneath an apple tree, flower of Kent variety if the later botanical records hold. An apple detaches, falls, strikes earth. But Newton is not watching the apple. He is watching its trajectory, perpendicular, straight toward the Earth's center. And that perpendicularity triggers the question, why should that apple always descend perpendicularly to the ground? Why not sideways or upwards? The question survives in William Stukeley's 1752 memoir. Stukeley dined with the 83-year-old Newton in 1726, just months before death, and Newton recounted the moment. The exact phrasing matters. Perpendicular descent, not just falling. Perpendicular implies directionality, implies a target. The Earth draws it, Newton reasoned. There must be a drawing power in matter. Not gravity, drawing power. The language reveals his thinking, something in Earth's matter pulls. And if the sum of Earth's drawing power concentrates at Earth's center, then every falling object aims for that point. Therefore, the apple falls perpendicularly, toward the center. This is the first step, recognizing that fall direction indicates a center of force. But here is where it gets interesting. If matter draws matter, Newton continues in Stukeley's account, it must be in proportion of its quantity. Therefore, the apple draws the Earth as well as the Earth draws the apple. Mutual attraction. Action and reaction. Before he formalized the third law of motion, the apple pulls Earth, Earth pulls apple. The forces are equal. But Earth barely moves because its mass overwhelms the apple's mass. The calculation is already forming. Most people stop there. Cute story, apple falls, Newton thinks. But the real leap has not happened yet. The leap requires extending that drawing power beyond the mountaintops, beyond the atmosphere, to the moon. This is not obvious. This is insane. Terrestrial physics did not apply to celestial bodies in 1666. Aristotle's cosmology still dominated. Earth was the realm of change, decay, straight-line motion. The heavens were perfect, eternal circular motion. Planets moved in crystalline spheres, different substances, different rules. To suggest that the same force making an apple drop also governs a celestial body required intellectual violence against centuries of accepted cosmology. Published 1638 in Discourses and Mathematical Demonstrations, relating to two new sciences, Galileo showed that horizontal and vertical motion are independent. A cannonball fired horizontally falls at the same rate as one dropped straight down, even as it travels forward. The trajectory is a parabola. This mattered, because if you fire that cannon faster, the cannonball travels farther before hitting ground. Fire it faster still. It travels farther, and Newton realized if you could fire it fast enough, the ball would fall but never hit the ground, because Earth's surface curves away. The projectile falls around the planet. This is orbit, not flying. Falling continuously while moving forward fast enough that you keep missing the ground. The moon is not staying up. The moon is falling. Forever. The thought experiment appears in Book 3 of the Principia, published 1687. The famous cannon on a mountaintop diagram, fire with increasing velocity. At sufficient speed, the projectile becomes a satellite. Newton drew this connection in 1666, during the plague years at Woolsthorpe. His own recollection, written circa 1715, states explicitly, "The same year I began to think of gravity extending to the orb." Of the moon. Extending. The word choice is precise. He is not discovering a new force for the moon. He is extending the known terrestrial force upward. Same mechanism, different distance. He knows the acceleration of falling bodies at Earth's surface, roughly 32 feet per second, later refined to 9.8 meters per second squared, but Newton worked with observational estimates. He knows the moon's orbital period, 27.3 days, recorded accurately by astronomers for centuries. He knows the moon's distance from Earth, roughly 60 Earth radii, about 240,000 miles or 384,000 kilometers in modern units. And he knows Kepler's third law. Kepler derived this empirically from Tycho Brahe's astronomical data. He did not know why it worked. It was a pattern observed in nature, but Newton in 1666 realized that Kepler's third law implies an inverse square relationship for the force. If period squared equals distance cubed, then force must vary as 1 over distance squared. The mathematics follows from centripetal acceleration. An object moving in a circle requires inward acceleration proportional to velocity, squared divided by radius. Velocity equals circumference divided by period. Substitute Kepler's relationship. The algebra churns. The force ends up proportional to mass divided by distance squared. Inverse square law. Error. Centers of their orbs. I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve. Sesquialterate, 3/2 power. Period to the 2/3 power equals distance. Flip it. Distance cubed equals period squared. The inverse square law drops out mathematically. This is 1666. Newton is 24 years old. He has derived the gravitational force law from Kepler's empirical observations using pure mathematics, but he has not yet proven it applies to the moon. The same. He knows Earth's radius, about 4,000 miles. The moon orbits at 60 Earth radii, 60 times farther. If gravity follows inverse square, the force at the moon should be 1 over 60 squared, 1 over 3,600. The moon should experience 1/3600th of Earth's surface gravity, does it? The moon travels 2 pi times the orbital radius every 27.3 days. Convert to seconds. The moon moves roughly 1,000 meters per second. Centripetal acceleration equals velocity squared divided by radius. Plug the numbers. The moon's acceleration toward Earth works out to about 0.0027 meters per second squared. Earth's surface gravity is 9.8 meters per second squared. The ratio is 0.0027 divided by 9.8, roughly 1 over 360. Close to 1 over 3,600. Not exact, but pretty nearly as Newton himself said. The force at the moon's distance matches the inverse square prediction from Earth's surface gravity. Same force, same law, different distance. Newton sat in Woolsthorpe Manor in 1666 with pen and paper and demonstrated mathematically that the force pulling the apple and the force holding the moon follow the same inverse square relationship with distance from Earth's center. The heavens and earth obey one law, one physics, one reality. The mental revolution is complete. He did not publish until 1687, 21 years. The delay has puzzled historians. Some claimed he lacked accurate values for Earth's radius. That explanation is probably false. Earth's circumference was known to reasonable accuracy by 1666. The more likely reason is conceptual. Newton had a problem. A sphere is not a point. Earth is not a mathematical center. It is a massive ball 4,000 miles in radius. The apple falls to the surface, not to some abstract central point. The moon orbits at 60 radii, but from what? Where exactly is the center of gravitational attraction for a distributed mass? This question tortured Newton for 2 decades. Center. This is not obvious. This requires integral calculus integrating over all the tiny mass elements in the sphere and showing they sum to produce the same force as a central point mass. Newton had invented calculus by 1666. He called it fluxions. But the spherical mass theorem took years to prove rigorously. Only after he cracked that problem did he have confidence to publish. The calculation worked in 1666. The mathematical foundation solidified later. Can you show me the proof? Newton says he worked it out years ago but cannot find the papers. He promises to send them. 3 months later, Halley receives a 9-page treatise, De Motu Corporum in Gyrum. On the motion of bodies in orbit, the proof is there. Inverse square gravity produces elliptical orbits exactly as Kepler observed. Halley recognizes genius. He urges Newton to expand the work, to publish everything. Newton retreats into obsession. 18 months of near total focus. His chemical notebooks, which normally have regular dated entries, go blank from May 1684 to April 1686. He stops eating properly. He forgets to sleep. His servant later recalled finding him standing in his room in the morning still wearing yesterday's clothes, having worked through the night. The manuscript grows. What began as 9 pages becomes 3 books. Book 1 establishes the mathematical framework, the laws of motion, the geometry of orbital mechanics under various force laws. Book 2 demolishes Descartes' vortex theory of planetary motion by showing fluid resistance contradicts observed celestial behavior. Book 3 applies the mathematics to the real solar system, planetary orbits, lunar motion, tides, comets. The universal law of gravitation emerges. Every particle of matter attracts every other particle with force proportional to the product of masses and inverse to the square of the distance. The manuscript survives today at the Royal Society Library in London. On May 19th, the Society votes to publish. Halley is appointed to oversee printing, but immediately problems emerge. Robert Hooke claims priority. He says he told Newton about inverse square gravity years before. Newton is furious. He hates disputes. He threatens to suppress Book 3 entirely, the book containing the actual cosmology and the universal gravitation law. Halley deploys diplomatic genius. He soothes Newton. He downplays Hooke's claims. He gently persuades Newton to continue. Meanwhile, the Royal Society has no money. They had just published Francis Willoughby's Historia Piscium, a lavish book about fish that nobody bought. The Society is effectively bankrupt. They are paying Halley his salary in unsold copies of fish books. Halley personally finances the Principia's printing. He pays Joseph Streeter, the printer. He designs the woodcut diagrams, he proofreads the Latin, he manages Newton's delays and revisions. The Principia is complete. Philosophiae Naturalis. Principia Mathematica. Mathematical Principles of Natural Philosophy. Printed in Latin. 3 books, 511 pages. Approximately 300 to 400 copies in the first printing. The book that unified heaven and earth. No calculus notation visible, though calculus underlies the derivations. Book 1 presents propositions about motion under central forces. Proposition 1, areas swept out by a radius vector are proportional to time. This is Kepler's second law derived from Newton's laws of motion. Proposition 11, if a body moves in an ellipse, the force is directed toward the focus and varies inversely with the square of the distance. This proves inverse square gravity produces Kepler's first law. Proposition 66, multiple bodies can orbit a central mass following Kepler's laws if the force is inverse square. The mathematics is ruthless. Theorem stacks on theorem, each proved rigorously. He shows that Descartes' theory of celestial vortices, where planets are carried by swirling invisible fluids, contradicts observed planetary motion. If planets moved through a resisting medium, their orbits would decay. They do not, therefore no vortices. This was a direct attack on Cartesian cosmology, which still dominated European thought. Newton demolishes it with mathematics. Book 3, titled The System of the World, applies the framework to astronomy. He starts with observed phenomena. The moons of Jupiter obey Kepler's third law around Jupiter. The planets obey Kepler's third law around the Sun. The moon orbits Earth. From these observations, Newton derives rules of reasoning. We should assign the same causes to natural effects of the same kind. The force holding Jupiter's moons follows the same law holding our moon. The force holding the planets follows the same law, and that law, calculated from observed motions, is universal gravitation. Every mass attracts every other mass, proportional to the product of masses, inverse to the square of distance. One law, one universe. He explains the tides as the combined gravitational pull of moon and sun on Earth's oceans. He calculates the precession of Earth's axis as gravitational torque from the sun and moon acting on Earth's equatorial bulge. He tracks comets, showing they orbit the sun in elongated ellipses, following the same gravitational law as planets. Halley later uses Newton's methods to predict that the comet of 1682 will return in 76 years. It does. In 1758, it is named Halley's Comet. The prediction vindicated universal gravitation. He refuses to speculate about how gravity works, whether it is transmitted by some medium or acts at a distance instantaneously. He says it is enough that gravity really exists and acts according to the laws explained and abundantly serves to account for all the motions of celestial bodies and of our sea. The mechanism is unknown. The mathematics is certain. The geometry was dense, but those who understood recognized its importance. The Marquis de l'Hôpital asked a mutual acquaintance, "Does Mr. Newton eat and sleep like other men? I picture him as a celestial intelligence." John Locke, the philosopher, wanted to understand it but lacked the mathematics. Halley assured him the mathematical proofs were sound. Locke accepted the conclusions on trust. On the continent, Leibniz and the Cartesians resisted. They disliked action at a distance. They wanted mechanical explanations, vortices, contact forces. Newton's gravity seemed like magic, an occult quality. How could the sun reach across millions of miles of empty space to pull the planets with no medium? Astronomers could predict planetary positions with unprecedented accuracy using Newton's laws. Engineers could calculate trajectories. The tide tables worked. By the mid-1700s, Newtonian gravity was accepted across Europe. The Principia was revised twice in Newton's lifetime. The second edition appeared in 1713 with a general scholium and corrections. The third edition in 1726, the year before Newton's death, edited by Henry Pemberton, with further refinements. Andrew Motta's English translation came out in 1729. The Marquise du Châtelet translated it into French in 1756, with commentary by Clairaut. Calculations by Urbain Le Verrier in 1846 pointed to where an unseen planet must be. Johann Galle found Neptune there the same year, gravitational perturbations made visible, but a tiny anomaly persisted. Mercury's orbit precessed slightly more than Newton predicted, 43 arcseconds per century unaccounted for. Astronomers proposed an unseen planet inside Mercury's orbit, Vulcan. Searches found nothing. The discrepancy remained unexplained until 1915, when Albert Einstein published General Relativity. Gravity is not a force, it is curvature of space-time. Mass bends space. Objects follow geodesics in curved space. Mercury's extra precession emerges naturally from the equations. Einstein's theory matched observation. Newton's law is an approximation valid for weak gravitational fields and slow speeds. Extremely accurate for most purposes, but not exact. Therefore, the hypothesis is supported. This is the scientific method crystallized. Observe, hypothesize, derive, test, repeat. Newton applied it with unprecedented rigor, and the stakes were cosmic, not just explaining one phenomenon, but revealing that all matter everywhere follows the same laws, that the universe is comprehensible, that mathematics describes reality, that human reason can decode nature's workings. The implications rippled beyond physics. If celestial mechanics obeys mathematical law, perhaps other domains do too. The Enlightenment flows from this idea: reason over tradition, observation over authority, the universe as clockwork governed by discoverable principles. Voltaire championed Newtonian science in France. Kant restructured philosophy around the Newtonian cosmos. The American founders designed government with Newtonian mechanics as metaphor. Checks and balances, laws of political motion. The scientific revolution becomes political revolution, becomes cultural revolution, all tracing back to a 24-year-old in a garden asking why apples fall straight down. If Halley had not visited in 1684, the Principia might never have appeared. Newton was content with private understanding. He disliked controversy. He found disputes distasteful. Philosophy is such an impertinently litigious lady, he wrote to Halley, that a man had as good be engaged in lawsuits as have to do with her. He nearly suppressed Book 3 over Hooke's priority claims. He delayed publication for 20 years because he could not prove the spherical mass theorem to his satisfaction. The mental process that unified reality almost stayed locked in one mind. It took Halley's persistence, diplomacy, and personal wealth to bring it to the world. The mechanist demanded explanations Newton could not provide. Action at a distance remained philosophically troubling. Only after decades of confirmed predictions did consensus form. The unification Newton achieved mentally in 1666 took the scientific community 50 years to accept. The cognitive leap was that difficult, the weight of Aristotelian cosmology that strong. Separating heaven and earth was not just physics. It was theology, it was metaphysics, it was the structure of reality itself. To merge them required not just calculation, but courage. The courage to trust mathematics over millennia of tradition. Proved that projectile motion follows parabolic paths. Observed Jupiter's moons proving not everything orbits Earth. But Galileo still kept celestial and terrestrial separate. He studied falling bodies on Earth. He observed planets through telescopes. He did not connect them with a universal force. Kepler had gone further. His 3 laws described planetary motion mathematically. But Kepler thought in terms of magnetic fibers streaming from the sun, pushing planets along their orbits. He imagined a physical mechanism. He did not conceive of action at a distance. He did not apply terrestrial concepts to the heavens. Descartes proposed vortices, swirling fluids carrying planets, a mechanical explanation, still separate from earthly gravity. He took Galileo's terrestrial mechanics and Kepler's celestial patterns and showed they are 2 aspects of one law. The synthesis required new mathematics, calculus to handle continuous change and infinite summation. It required new physics, the laws of motion generalizing Galileo's insights, and it required conceptual audacity, the willingness to say that the cosmos is not divided, that one set of laws governs all matter from pebbles to planets. This was not just science, this was ontology, a new picture of what exists and how it behaves. The inverse square of distance, the universality. And the gravitational constant g, the number that sets the strength of gravity, Newton never measured. He could calculate ratios, the sun's mass in Earth masses, Jupiter's mass in sun masses. But the absolute value of g requires measuring the gravitational force between laboratory scale masses. That did not happen until 1798, when Henry Cavendish performed the famous experiment with lead spheres on a torsion balance, 111 years after the Principia, 71 years after Newton's death. Only then could g be determined. 6.6, 7 times 10 to the negative 11, Newton meters squared per kilogram squared, a tiny number. Gravity is by far the weakest of the fundamental forces, yet it shapes the cosmos because it acts on all mass and is always attractive. Newton lived another 40 years after the Principia. He left Cambridge in 1696 to become warden then master of the Royal Mint. He reformed England's currency with ruthless efficiency. The recoinage of 1696 through 1699 replaced old hammered coins with machine-milled ones. Newton oversaw the entire operation, 4 million pounds sterling processed. Thousands of workers employed at the Tower of London Mint. He introduced quality controls. He tracked down counterfeiters personally. He interrogated suspects. He gathered evidence. He sent over 24 counterfeiters to the gallows. His prosecution papers survive. Cold, detailed accounts of crimes and punishments. This was Newton, the administrator, applying the same precision to currency that he applied to celestial mechanics. He was elected president of the Royal Society in 1703, holding the position until his death 24 years later. He dominated the society. He settled disputes. He promoted experiments. He feuded with rivals. The presidency gave him institutional power to shape British science. He published Optics in 1704. His work on light and color delayed for decades to avoid controversy. The book appeared in English, not Latin, reaching a broader audience. It proposed that light consists of particles or corpuscles, an idea later challenged by wave theory but vindicated in modified form by quantum mechanics. Optics included queries about the nature of light, matter, and force. Speculative questions Newton would not risk in the mathematical Principia. The queries influenced generations of experimenters. He engaged in bitter priority disputes with Leibniz over who invented calculus. The dispute turned ugly. Newton used his position as Royal Society president to appoint a committee investigating priority. The committee, naturally, ruled in Newton's favor in 1712. Newton may have written part of the committee's report himself. Leibniz died in 1716, embittered. The dispute poisoned relations between British and continental mathematics for decades. British mathematicians clung to Newton's fluxion notation, while Europeans adopted Leibniz's superior differential notation. British mathematics stagnated as a result. The continental school advanced. The costs of Newton's vindictiveness rippled through generations. He dabbled in alchemy and biblical chronology, fields now considered pseudoscience but central to his worldview. His alchemical manuscripts, discovered centuries later, shocked historians. Millions of words on transmutation, the philosopher's stone, hidden properties of matter. Newton was not a rationalist in the modern sense. He believed in hidden forces, divine action, secret knowledge encoded in Scripture. His biblical chronology attempted to reconcile ancient history with scriptural accounts, published posthumously as The Chronology of Ancient Kingdoms, amended, speculative, influential in its time, now forgotten. Newton's mind contained contradictions. The man who formulated universal mathematical laws also sought mystical wisdom in alchemical symbolism. The compartments did not communicate, or perhaps they did. Perhaps his belief in hidden connections drove his search for universal principles. Perhaps the mysticism and the mathematics were two approaches to the same question. What is reality? What unifies it? He was buried in Westminster Abbey with state honors, the first scientist so honored. The funeral was attended by nobility, scientists, government officials. Voltaire, visiting London at the time, observed the ceremony and marveled that England honored its natural philosophers like France honored its military heroes. The inscription reads, "Let mortals rejoice that there has existed such and so great an ornament of the human race." The tomb remains a pilgrimage site for scientists and tourists. The planets are balls of gas or stone following the same physics as cannonballs. The universe is one system governed by discoverable laws. This changes everything. It makes science possible as a universal project. It makes engineering possible based on reliable physical principles. It makes the cosmos comprehensible rather than mysterious. Observe the apple falling perpendicularly. Ask why perpendicular. Deduce a central attractive force. Hypothesize it extends beyond Earth's surface. Calculate whether it reaches the moon. Use known observations, moon's orbit and period, and Kepler's laws. Derive the force law mathematically. Test the prediction. The numbers match. Conclude the same force governs both. Extend to all matter. formulate universal gravitation. Spend 20 years proving it rigorously, publish when pushed by colleagues, watch the scientific community slowly accept over decades. This is not a flash of insight. This is a sustained intellectual campaign. Observation to hypothesis, to derivation, to test, to proof, to publication, to acceptance. The structure of scientific progress. Newton built the template. You can see Humphrey Newton's handwriting, the compositor's marks, Halley's marginal notes, Newton's corrections. The document that changed the world is physical ink on 17th century paper. Fragile, preserved, digitized now, accessible. The calculations are there in Latin and geometry. Anyone with a mathematics can follow the reasoning from falling apples to universal law. The mental process is replicable. That is the point. Newton did not perform magic. He performed systematic reasoning. He asked the right questions. He had the mathematical tools. He did the work, and reality yielded. String theory and loop quantum gravity compete without decisive evidence. The search for unification continues. But Newton showed it is possible. Disparate phenomena can share common causes. Mathematics can reveal hidden connections. The universe has structure we can understand. And the process starts with noticing, why does the apple fall straight down? The question that unified heaven and earth. The question that redefined reality. In the final accounting, the mental process is this. First, close observation of the commonplace, not just seeing the apple fall, but seeing its trajectory, its perpendicularity, the precise behavior. Second, questioning what everyone takes for granted. Why straight down? Why not sideways? What determines the direction? Third, proposing an explanation, a drawing power in matter, a central force. Fourth, testing whether the explanation extends beyond immediate experience. Does terrestrial gravity reach the moon? Fifth, using existing knowledge. Kepler's laws, orbital periods, measured distances. The moon test required no new observations. Sixth, rigorous mathematical derivation. Showing inverse square law follows from Kepler's third law, calculating the expected acceleration at the moon's distance. Seventh, verification. The calculated value matches observed motion, pretty nearly. Eighth, generalization. If it works for the moon, it works for all celestial bodies. Universal law. Ninth, spending years on mathematical rigor, proving theorems about spherical masses and elliptical orbits. 10th, reluctant publication only under external pressure. Finally, waiting for the world to catch up. Decades for acceptance. This multi-step process, observation to question to hypothesis to derivation to test to rigor to publication to acceptance, this is the method that unified heaven and earth. Not a moment of genius, though genius was required. A sustained, disciplined investigation. Newton worked on this for over 2 decades, from 1666 to 1687, counting only the period documented in his own recollections and correspondence. The apple story is true in essence, but misleading in implication. It was not an instant revelation. It was the beginning of a long calculation, the starting point of a mental journey that reconstructed reality, and the journey was taken alone, in isolation. First forced by plague at Woolsthorpe, then chosen by temperament at Cambridge. Newton worked in solitude. He shared little. He published reluctantly. The unification happened in his mind before it happened in the world. The instant he realized heaven and earth are one. That realization, preserved in Stukely's memoir written 1752, published decades later, that realization is the key, because it shows the process. How a mind moves from observation to question to unification. How human reason confronts the cosmos and wins. How mathematics strips away illusion and reveals structure. This is what changes how you see reality. You know it is falling, perpetually falling around Earth, held by the same force that would pull you down if you jumped. No crystalline spheres, no quintessence, rock and dust and gravity. The ground beneath your feet and the celestial bodies overhead, they are made of the same stuff, obeying the same laws. There is no division, no separate realms, one physics, one reality, one universe. Newton's mental process proved this. And the proof sits in the library at Cambridge, a manuscript in Latin. 3 books, 500 pages, calculations that unified heaven and earth. That is how you see reality differently. You understand that what seems separate might be the same, that the patterns are there if you look, that mathematics can reveal them, that human minds can grasp cosmic truths, and that it starts with noticing what others ignore, an apple falling straight down. The question nobody else asked, the calculation that changed the world.